Okay, folks, we can get started. Any questions before I get going on stuff? The motor circuit debugging seems to be going relatively well. I've seen about every bug that I can imagine, but I suppose that's to be expected. But most people seem to be getting through it, and hopefully gaining an appreciation for how challenging it is to build something. That's part of the goal here. The other thing I wanted to remind you about before we get going is that your final project proposals are due next week. I'll post a thing on Canvas to just remind you, but what that implies is that if you're in the Monday section, I'm going to be looking for a proposal on Monday. So if folks would like to talk about project ideas or kick any around, I'd be very delighted to if you want to come to lab and we could chat about it. The project proposals, I'll just mention, I have some information about them on the web page here. Let's see, project proposal that describes what we're looking for in it. There's not a lot to these. Like I said previously, it's maybe a one-pager or a two-pager in which you essentially lay out the idea. What we are mostly checking for here is that, first of all, you're not proposing that you are not proposing to do anything that is going to pose bodily harm to you or potential risk to the building. No flamethrowers, no fast projectiles, that kind of thing. But the main thing that we're checking for here is scope. It's really easy to propose a project that's accidentally a PhD dissertation, and it's also really easy to propose a project that's accidentally a weekend effort. And so what we're mostly going to help you do by way of these proposals is take your idea and get it scoped correctly for the amount of time that we have available. But like I said, give it some thought because it's a long project and it's a big undertaking, and it's a whole lot more fun if you're doing something that's really interesting to you. If you're still trying to come up with ideas, you might consider the mechanism that I quite like for coming up with project ideas that we talked about previously. Make a big list of everything you're curious about. You don't have to know anything about it. It doesn't have to be related to engineering at all. Just make a list of everything that you'd like to learn more about. And then on your own or together, I'd be happy to help brainstorm some engineering projects that could be the mechanism by which you learn about this interesting thing that you're curious to learn about. Those kinds of projects are delightful. But of course, any kind of project that you'd like to do, so long as it's appropriately scoped and challenging and so forth, is perfectly fine. Any questions about that before I get into content for today? We have low attendance today. I heard that it might be St. Patrick's Day influence. Yes?
When it comes to like external or like parts that might be interesting, like Bluetooth, stuff like that.
Yeah.
That's
a great question. So to the extent that your project requires stuff, components and materials and so forth, I will be happy to buy such things for you up to $25 per group. I'll post a form where you can say, please order us these things, and I'll do it on a date that I'll specify. I'll probably do 2 rounds of those because we'll do the first round and then everyone will go, oh my God, I forgot to order this thing. And then we'll do another round. I'll cover up to $25. The total cost of the project, including that which you contribute, should not exceed $125. The reason for that is we don't want people like wheeling in motorcycles into the lab to work on or something like that. We want the total project cost to not exceed $125. Yeah.
Sorry, as I was thinking about how to phrase this, you might have actually answered it. Can we do the whole like ask the makerspace club for $100 thing for this project, or is that not really it?
Please don't ask the Maker Club for it. The Maker Club is a sacred place purely for passion projects. Should not have any class projects associated with it. Yeah, yeah. Bruce?
You have Bluetooth chips in the lab. If you need Bluetooth, then don't buy it.
Yeah, did you hear that? So to answer your question, you can use a Pico W if you want Bluetooth or Wi-Fi or something. Okay, and we have those in lab. You don't need to buy those. 100 tiny motors? Those we'll buy. Okay, anything else before we get going? Yes?
Oh, so kind of with the $125 cap. So like if you had a like extraneous part that like, let's say like you want to do a music project with an instrument and you already have it, would that be allowed or like, you know?
Talk to me about the specific situation. Possibly,
Oh,
possibly.
Or like just like in general.
There is this general rule, but if there's a specific situation that might be extenuating or special in some case, I'm open to talking about it. Bruce?
One of these rules for council doesn't come out of previous abuse. come in with brand new stuff saying, oh, I own it. So, I got zapped. But if you bring in a piece of equipment that's obviously beat up and has had some serious use, then I think it's worth considering.
The other special case that I'll just mention, and then we'll get into this, is if you're doing your project in collaboration with a research group here, like perhaps you work in a research lab and you want to do a project related to that lab, then the cost limitations are lifted. Okay, anything else before we get going? Okay, that being the case, let me just very briefly remind you what we've been doing. So I'll remind you that last week, you guys built the motor circuit, you got it interacting with the PWM output of the RP2040, and with those two things in place, you could do open loop control of the motor. And that was or is your checkoff for this week, is to demonstrate open loop control of the motor. And now we're closing the loop. Closing the loop means that we need to read the IMU, the accelerometer and gyroscope sensor. We read that sensor by way of an I2C channel. So the last conversation we had was about I2C and how we actually talk to this thing. The sensor gives us not arm angle, which is what we want and what we're going to close a loop around. Instead, it gives us acceleration and angular rate. So the next conversation that we're going to have today is about how we use those two pieces of information, which are not arm angle, what we want, but are related to it, in order to generate an estimate for arm angle. And then Monday and Wednesday of next week, we're going to talk about how we use the output of that filter, your estimate for arm angle, as an input to a PID controller to drive the error between where the arm is presently located and where you want for it to be to 0. Okay? So let's talk about this complementary filter. I want to have this conversation by way of your reading for this week. There's a document here that describes these filters. Like I mentioned, what this filter is going to do is combine information from an accelerometer and from a gyroscope. And I want to approach this by thinking about the information coming out of each of those sensors independently. And then we're going to talk about how we combine those two into an estimate for arm angle. So let's start with the accelerometer. What we're looking at here is a picture, kind of like the picture of what we're building in lab. You probably are going to measure angle relative to straight down as opposed to straight up, but okay, it's the same kind of idea. So we have a pivoting arm here, and there's an angle represented here, and then on this arm there's an accelerometer and a gyroscope. And the accelerometer, when it's just, when the accelerometer is just, when this arm is not accelerating, what the accelerometer is essentially telling us is the direction of acceleration due to gravity. So essentially, the accelerometer is measuring a vector, and that vector points directly to the center of the Earth. Okay, it's measuring gravity, sort of. I'm going to come back to this in just a moment, but it's measuring gravity. And by way of only the accelerometer output, we could generate an estimate for the angle at which the arm must be hovering by way of a little bit of simple trigonometry. So you can imagine that, if our accelerometer here and our arm is here and our arm is oriented like this, right? Our gravity vector is pointing straight down. In the local frame of the accelerometer, if we assume it's oriented with axes that look like this, we're going to measure that acceleration in some combination of this accelerometer's y and x axes. So we could deploy just a little bit of trigonometry and say, okay, well, if we're interested in this angle right here, that would be the arctangent of the x component of our measured acceleration and the y component of our measured acceleration. And by way of that arctangent, we would arrive at this angle here. What this is showing you, which by the way it is not of relevance for this lab, but I'm pointing it out because it's good to know for like inverted pendula sorts of applications, is if the range of angles over which we were trying to estimate and control this arm were very small, then we could approximate that arctangent by way of a small angle approximation to just being ax over ay. Because our arm is swinging through a full, essentially 180 degrees, we cannot use this small angle approximation. You will estimate the angle of the arm by way of the accelerometer using the full arctangent there. So you might ask, if we can get the angle that we are interested in by way only of the accelerometer, why even incorporate the gyroscope? What is the necessity of doing a complementary filter if apparently it's the case that the information that we care about is encoded in the accelerometer output alone? Does anybody know the problem? Does anybody know why this wouldn't work? Noise. The accelerometer is noisy. Now, when you first start implementing this complementary filter, I recommend that you do so without the motor running so that you can just lift the arm to different angles and see if the output looks the way that it's supposed to look. And when you do that, and you're observing the traces coming out of the accelerometer on the screen, they're going to look a little bit noisy, but you might not believe me that they're so noisy that you couldn't close a control loop around it. But the moment that you turn on that motor, what you will observe is the noise coming out of the accelerometer explodes. The reason for that, of course, is the arm is vibrating the motor, generating very high frequency accelerations. This sensor is sensitive to all those accelerations, and you see this tremendous amount of noise coming out of the accelerometer. So much noise that it would be impossible for us to control the motor using only that sensor. But the noise has a very special and very useful property, which is that it's zero mean. So the output of the accelerometer, you could interpret that as the true value of the acceleration, known only to God and the universe, plus some noise, but that noise that we're adding on to that true acceleration is well approximated as being zero mean Gaussian white noise. That's a very nice property. It's a property that is not shared by the other sensor in question, the gyroscope. So though the values coming out of our accelerometer are tremendously noisy, they are zero mean. Now there's a small caveat here that I'm going to come back to. The values coming immediately out of the sensor are zero mean. AX is zero mean. AY is zero mean. Is the arctangent of AX over AY zero mean? That's a nonlinear function. And so indeed it is not. I'm going to come back to that. We need to do just a little bit of footwork to manage that fact, okay? But the theta there is not going to be zero mean. It's going to have some bias introduced by the arctangent. But the values coming directly out of the accelerometer are in fact zero mean. So this has some properties that we like, zero mean, noise, but some properties that we don't like, a tremendous amount of noise. So we need to incorporate some information from another sensor, the gyroscope. The gyroscope has its own set of nice properties and its own set of annoying properties. I'll remind you that what the gyroscope is telling us is angular rate. It has no idea about its absolute angular position. It only knows how quickly it's rotating. So that is to say, the arm could be held fixed, steady at this angle, and you would be getting 0 out of your gyroscope because it's not rotating. As you then move it down, you'll get non-zero measurements out of this axis of the gyroscope. And when you hold it steady, you will again get 0 out of your gyroscope because the arm is not moving. The gyroscope only measures angular rate, degrees per second. But that's okay. We can use an estimate or a measurement of degrees per second in order to maintain an estimate for angle, in principle, by numerically integrating it. So you could imagine that we could say, you know, when we turn on our system, we're going to imagine that the motor is hanging straight down, approximately. Okay, maybe that's an angle of 0 degrees, depending where you're measuring your angle relative to. And then once it starts lifting, you're going to measure some angular rate, and you might imagine that we could maintain an estimate of where the arm is located, its angular position, by Euler integrating the output of the gyroscope. So that is to say, our new estimate for our angle would be equal to our previous estimate for our angle, plus our gyro output times delta t, right? This is the same kind of Euler approximation that we talked about a little bit in connection with Lab 1, when we were talking about integrating those curves as a very efficient way to compute them. But this has its own set of problems. What would be the problem with this approach? If we were only to use the gyroscope to maintain an estimate for angle, what problem would we start to see?
Maybe some form of like overshooting or like, I don't know.
It's a good guess. Ultimately, probably. But before anything overflowed, what you would certainly see is a bias begin to accumulate. That bias would come as a consequence of numerically integrating a noisy output. It also is an inherent property of these gyroscopes. You can get the most expensive gyroscope that you want. The LN200, it flies on a lot of flagship spacecraft. You can buy the LN200 or you can buy a pretty nice house. That gyroscope develops a bias. They all develop a bias, something inescapable about these things. So the nice property of the gyroscope is it's very low noise as compared to the accelerometer. And you'll observe this when you start messing around with this. You turn on the motor and start moving this thing around. The traces coming out of the accelerometer, the raw measurements from the accelerometer, are all over the place. The gyroscope has nice, clean outputs, but if you observe it for long enough, you'll watch those outputs drift. So each of these two inputs to our complementary filters have some properties that are nice and some properties that are not nice. Nice property of the accelerometer, zero mean noise, no bias. Bad property of the accelerometer, highly noisy. Nice property of the gyroscope, very low noise as compared to the accelerometer, but a bad property is it develops a bias over time. The complementary filter is a mechanism by which we can retain the good properties of each of these two sensors and mitigate each of their bad properties. I'm going to talk to you now about how that works. But are there any questions before I do about the accelerometer in isolation, the gyroscope in isolation, and why this wouldn't work just using one or the other, why we actually have to fuse information from the two? Let me mention too, before I show you this, that estimation is a whole field of study. Like so many things, it's a rabbit hole that goes pretty much infinitely deep. The complementary filter might be, many folks would classify this as a pretty quick and dirty way of doing this, but for our purposes, it works just fine. But if you are interested in estimation stuff, I will just point you to, there is some reading down here. Particle filters, sigma point filters. This describes a whole bunch of different estimation algorithms that if you find yourself kind of interested in this as a principle or as a field, you could read about. Kalman filters, sigma point filters, particle filters, all that kind of stuff. We're using the relatively speaking quick and dirty complementary filter. Okay, so how does this work? Looks like the following. Where will all of this stuff that I'm about to describe live in your code? You can imagine that everything I'm about to describe lives in your interrupt service routine. What I'm about to describe is part of the time-sensitive control process that you must have execute 1,000 times a second. So the stuff I'm about to describe lives in the interrupt service routine. And we can read this order of operations from left to right. So we enter our interrupt service routine. The first thing that we do when we enter that interrupt service routine is gather a batch of raw measurements from our accelerometer and from our gyroscope. Okay, so we gather AX, AY, and AZ, and we gather our gyroscope measurements, which of course also come in 3 dimensions. We're only going to actually care about the one about which we're rotating, right? We gather our raw measurements, and then let's focus for the moment on the top branch of this flow chart. For our accelerometer measurements, we'll take those, and we will use 2 of the 3 accelerometer readings, right? We'll use the accelerometer readings in the 2 dimensions that are exchanging the gravity vector as this rotates in order to compute the accelerometer's best guess for where the arm is presently located based on the measurements that it just got. This is going to be noisy. Now, in this flow chart uses that small angle approximation to get an accelerometer angle here. Just remember, you all have to use the full arctangent, the full inverse tangent to compute this because we're going through a full 180 degrees of rotation here, okay? So we gather our raw accelerometer measurements. We use those accelerometer measurements to compute the accelerometer angle, okay? And then we're going to talk about this in a moment. But on this top branch, we've got the accelerometer's best guess for where we are. Then on the bottom branch here, we're going to take our gyroscope reading. Remember, this is a rate, degrees per second, and we're going to multiply that, our degrees per second in the axis of rotation, by dt. How frequently are we taking these measurements? In your case, if you're running your PID controller at 1 kilohertz, dt is going to be 0.001 seconds. So if you take your rate and you multiply it by dt, that gives you your gyro angle delta. That is to say, this is the gyro's best guess for how many degrees we have moved in the previous time step. Since the last time we gathered a measurement, we have moved this many degrees. We then take that and we add to it our previous output for the complementary angle. So we say last time we did this, we guessed that we were at 45 degrees. Our gyro measured a delta of 2 degrees, and so we add the two and we say the gyro now thinks we're at about 47 degrees, or whatever it may be. So at this point now, we have the accelerometer's best guess for where we are presently located based on the measurements that it just gathered. We have the gyro's best guess for where the arm is presently located based on the data that it just gathered added with our previous output of the complementary angle. And now we want to combine the two. And we combine the two in this complementary filter by way of a simple weighted average. So we take some accelerometer weight, a number between 0 and 1, multiply it by the accelerometer's best guess for where we are, add that to our gyro's best guess for where we are, multiplied by its own weight, a number between 0 and 1, and we add the two together to arrive at our new complementary estimate for where the arm is presently located. 1/1000th of a second later, we do it again. It's this that becomes our input to the PID controller. We'll compare this output for where the arm presently is, the estimate for where we are, against where we want to be. That error is the input to our PID controller. Now these weights, incidentally, we will choose these weights in order to retain the nice properties of each of these two sensors and to mitigate their bad properties. We'll make the gyro weight something quite high, that is to say, something on the order of maybe 0.99, maybe 0.999, a number very close to 1. We're going to make the accelerometer weight, the two sum to 1, you know, the complement, 0.01 or 0.001. If you think about this for a moment, you can convince yourself that by choosing weights of these two values, what we're effectively doing is high passing the gyro and low passing the accelerometer, which is exactly what we want. The gyro, over a long period of time, develops a bias, but over short periods of time, it has much less noise than the accelerometer. You can twitch the arm very quickly, and the gyro responds very quickly. You'll be able to see this on the VGA screens. But it develops this bias. So by high passing this, we attenuate out all that low frequency bias that it accumulates, and we just listen to it over the short term. That's where it's accurate, over the short term. Meanwhile, the accelerometer has so much noise on it that over the short term, we're not learning much from it. It's all over the place. But over the long term, it does not develop a bias. And so we low pass this, which prevents us from developing the bias that the gyro would develop over time. As you play with this, what you'll observe is if you make the gyro weight greater and the accelerometer weight smaller, what you'll observe on the output of your complementary angle is less noise, more bias. This is the knob we're tuning in the game that we're playing. We're trying to find the place in this search space that satisfies us as far as our application is concerned. The more you weight the gyro, the less noise you get, the more bias you get. The more you weight the accelerometer, the less bias you get, the more noise you get. I'll just mention as an aside that in like a high stakes application of an estimator like this, let's say you're flying a spacecraft or a jet or something like that, the way that folks often handle the gyro bias is that bias becomes an additional state that we estimate. In our case, we're not doing that, okay? But if you look at papers related to spacecraft and jets and so forth, what they're essentially doing is adding an additional state, x, y, z, x dot, y dot, z dot, gyro bias. And that becomes something that we estimate from time step to time step, okay? But I said, once we use the inverse tangent to approximate the accelerometer here, we do develop a bias. So we have to mitigate this a little bit. The way that we mitigate that is before you compute that accelerometer angle, what I recommend you do is low pass the raw measurements. And we talked in a previous lecture about a very quick and dirty, relatively simple way to do this. I think I have it linked here. Let me just see. Yes, you need to low pass this. It's a one-liner. Now the names of the variables in this line, but they're named in connection to the other place that you'll be applying a low-pass filter in this lab, which is displaying the output of your PID controller. Okay. But in this case, what this is essentially displaying is you could, let's say that we're filtering the X acceleration output from the accelerometer. This would read as filtered X equals filtered X plus raw measurement in the X direction minus filtered X right shifted by some amount. The more you right shift, the more low passing that you're doing here. And if you're squinting at that and you can't quite see how this is doing low pass, down just a little bit further on this page, I've showed you this before, but that expression is derived from an RC low pass filter. So you can see that indeed that must be doing low passing. Okay? So that's how I recommend that you mitigate that noise, or I'm sorry, that bias being introduced by the nonlinear ATAN2 function here. Now there are some gotchas with this that I want to go through. Are there any questions before I get to those? So it ends up really being a weighted average between the accelerometer's guess for where we are and the gyro's guess for where we are. And we choose the weights in order to high pass the gyro, low pass the accelerometer. That mitigates the bias from the gyro, but keeps its short time period accuracy. It mitigates the short time period noise of the accelerometer, but maintains its long-term zero bias nature. Okay. Speaking of projects, I have a project idea for somebody. How about a little system that sits on top of the projector with a camera that sees a face and then put a Pico between the HDMI plug there and say a VGA input there that will blank out the pixels here. So that wherever I walk, this isn't in my eyes and I have a square shadow behind me. I think you could do that. Okay, so then I want to talk through some details. I will warn you, if you go through and blindly apply the stuff on this web page without thinking about it, I promise that it will not work for you. The reason for that is, though all of this, everything described here is true, there's a sensitivity which may occur to you, which is, where am I measuring this angle relative to? Am I measuring it relative to straight up, or to horizontal, or to straight down? And furthermore, what is the orientation of my accelerometer, my IMU, on the arm? Do I have it oriented this way, or on the back this way, or on the back this way? There's 4 orientations where you could have the IMU on there. None of those orientations are any more or less correct than any of the other orientations, but you need to know the orientation of your sensor on your arm in order to determine these angles correctly. So you have to actually stop and think about this, probably with a pencil and a piece of paper, and draw out these triangles to make sure that you're computing these things right. And some of this is a little counterintuitive, so I thought I would go through it. So probably for many of you, you probably want to measure this angle. It doesn't really matter. You can measure whatever, you can do this relative to whatever reference direction you care to, but perhaps many of you will want to measure angle relative to straight down, so that when the arm is hanging straight down, it's at 0 degrees, horizontal would be 90 degrees, straight up would be 180 degrees, right? So we're measuring that angle. If we're measuring that angle by way of our accelerometer, so we're interested in getting the accelerometer approximation to this angle, what we are interested in is the arctangent of this leg of this triangle over this leg of this triangle, alpha over beta. These, of course, right, these are some pair of measurements coming out of our accelerometer, but depending on the orientation of our accelerometer, these might be z and x measurements, z and y measurements, z and minus y, z and minus x, right? It depends on the local frame of that accelerometer. So let's think through this a little bit. And by the way, what I have here is sort of the mathematical expression, and then this is the more C-like version of that expression that you'll probably implement in your interrupt service routine, okay? So let's think through this. Which measurements from the accelerometer are actually represented by those parameters alpha and beta? Well, like I said, you are attaching this accelerometer to your arm. The lab write-up makes no specification as to the orientation of this sensor. And it's got the little plugs on both sides, right? And so you may have put it on this way, you may have put it on this way, you may have put it on the back in this way or this way. All those are perfectly fine, but you need to actually look at it and figure out which orientation that you've chosen. And what you need to look at in particular is if you squint at the silk screen, you'll see that printed on the silk screen here, this tells you the directions of the positive X, Y, and Z direction as measured by that sensor. So if you look very closely, you'll see that there's a little X with an arrow pointed this way, a Y with an arrow pointed this way, and a Z with an arrow pointed out. Right? So it's a right-hand orthogonal coordinate system, X, Y, Z, pointing out. But of course, we could have put it on upside down, in which case Y would point straight down the arm, and X would point, that direction. Z would still point up. And either of those would work, but we would need to think about this. So this orientation is represented pictorially here. So you can see we're looking now edge on at this arm, and what we're seeing is the Y local direction points back towards the hinge, Z points straight up, X points into the board for this arbitrary orientation of the IMU. So if we had chosen to put the IMU on in this orientation, then those parameters alpha and beta we could imagine if we hold this straight up, we know that what we want this measured angle to be is 90 degrees in this orientation, right? And so we know that we want our alpha term to be 1, we want our beta term to be 0. The question is, for this orientation, which outputs of the accelerometers do alpha and beta correspond to? You could think about this, and this is the counterintuitive thing that I wanted to just bring up, okay? Let's suppose that we're holding this in this orientation, okay, and the accelerometer is right on top. Z's positive direction is straight up, and it's not moving. And I talked to some of you about this in lab already. If I talk to you about it, don't answer just yet, because I want people to think about it. Okay, so let's say we're sitting here, our accelerometer is resting there, and we're measuring gravity. So that is to say 1g of acceleration through the x-axis. Will we measure positive acceleration or negative acceleration? It's measuring gravity. It's measuring acceleration due to gravity. If you guess, you've got a 50% chance of getting it right. Yeah? Negative? Anybody disagree? Indeed, you will measure positive acceleration. Why? Why would you measure positive acceleration? Okay, here I'd like to offer you a thought experiment. Let's suppose that our accelerometer were glued to the bottom of an elevator floating in the vacuum of space, in free fall. Not accelerating, right, just floating around. Does it stand to reason that in that situation, the measurements that we would be getting out of that accelerometer would be 0? There's no forces acting on this thing, so there's no accelerations on this thing, and hence the accelerometer, which measures acceleration, would be measuring 0 acceleration. If we put a rocket booster on the bottom of this elevator and accelerated it up at 9.8 meters per second, you've all had this experience in an elevator. When it accelerates up, you get pressed against the ground, right? If we accelerate up at exactly 9.8 meters per second, what this accelerometer would feel is Earth gravity. It would be indistinguishable from Earth gravity. Down, right, pushing it into the ground. And so that is to say acceleration in this direction is indistinguishable from the experience of sitting here on the surface of the Earth in the presence of Earth gravity. So getting pulled down towards the center of the Earth, the accelerometer will measure acceleration up away from the Earth. This, by the way, delightfully, this is the thought experiment that Einstein used when he realized that gravity is acceleration, that those two are the same thing. Because he realized that if he was standing in this situation in an accelerating box in space, he would have no knowledge that he was not standing on the surface of the Earth. It's just to say to be careful, right? Because the orientation of these things matter. You might intuitively think that you'd be measuring negative 1g of acceleration here. Indeed, you'll be measuring positive 1g. Okay, so in this particular case, for this particular orientation of the sensor, the relevant outputs of the accelerometer here that we would use to compute that angle would be AY and AZ. AZ pointing up, AY pointing here. Okay. Likewise, if it was hanging straight down, you could see that using AY and AZ, we arrive at, correctly, 0 degrees in this orientation, right? But there's nothing correct or incorrect about this orientation as compared to other orientations. What if we had put it on upside down, or just opposite the direction that we just considered? So now the positive y direction points down along the arm, z still points up, and x points out at us, out of the board. The accelerometer is still measuring the same vector. It's just in its local frame, that vector looks like it's going in a different direction. And so in this orientation, rather than using AY and AZ, we would compute the arctangent of minus AY and AZ in order to arrive at the angle that we're looking for. So before you start turning the crank on that complementary filter, stop, stare at your sensor, figure out which axes you've chosen or selected, so that you make sure that you compute that accelerometer angle correctly. This also, incidentally, applies to the gyroscope. As this arm rotates up and down, let's suppose this orientation of the sensor, illustrated by those axes there, about which axis is the gyroscope rotating? Y points down the arm, Z points up, X points right out at you. X. Indeed, it points in the X direction. And furthermore, remember that by right-hand rule, positive rotation in the X direction would be this way. So in this orientation, as the arm lifts, we're going to be measuring positive X rotation. As the arm falls, we're going to be measuring negative X rotation. But like I said, there's nothing correct or incorrect about this orientation as compared to others. If we had put this on in the other direction, such that X faces into the board, then lifting the arm would give us negative readings out of the gyroscope. Dropping the arm would give us positive readings out of the gyroscope. The reason this is important is that when you compute the complementary angle, right, you're computing the gyro angle delta as being the product between the X output of your gyroscope and the time step between measurements. So the first index here of that array is going to be the gyro X times 0.001. That's how many degrees we've moved in the last 1/1000th of a second. But then we combine that by way of this weighted average with the accelerometer information, and notice that we subtract the gyro angle delta from the complementary angle. But that subtraction, maybe it's a subtraction or maybe it's an addition. It depends on which orientation you've put the sensor onto the board, right? If we put this on the opposite direction, or I'm sorry, in this orientation, this should indeed be an addition here instead of a subtraction, right? Because as we lift it, that's positive measurements out of the gyroscope, assuming that we want for the angle to increase on the way up, right? Other orientation, this is a subtraction because the gyro will measure negative rate as we lift and as the angle increases. Let me ask you this. let's suppose that you get the accelerometer angle right, but you mess up the gyro. Given the conversation that we just had about what the complementary filter is doing, what would be the symptom that you would see? So let's suppose you're plotting the complementary filter output onto the VGA screen, right, in sort of that oscilloscope fashion. So you're observing angle as a function of time. And let's suppose that the arm is perfectly steady at some orientation, and then you move it quickly to a new orientation and hold it steady. You've got the accelerometer right, you've got the gyro wrong. What will you observe? This is worth knowing because many of you will have this bug. Yeah?
When you move the new angle, would it remain like stable there, but like a completely wrong angle?
Not quite. Remember, we're high passing the gyro, we're low passing the accelerometer. So we're holding steady, moving quickly to a new angle, holding steady, which is a test that I recommend you all do for your complementary filter. What you would end up observing, given that you've got the gyro sign wrong, is let's say you move it quickly in the positive direction. What you would see in the complementary filter output is your angle estimate would dip in the opposite direction because you're high passing the gyro. But then once you hold it steady for a while at the new orientation, because you're low passing the accelerometer and you've gotten the accelerometer right, it would slowly then approach the correct orientation. And so if you move it and you see the complementary output do something like whoop and then back down to where you're supposed to be, or in the opposite direction go whoop and then up to where you're supposed to be, that is telling you you've got a sign wrong on your gyro. What about the opposite error? You've got the gyro right, but you've got the accelerometer wrong. In that case, you'd kind of observe the opposite, right? You'd move it quickly and you'd see it twitch in the correct direction, but then it would start drifting the wrong way. What you should see out of your complementary filter is very reactive estimates for where the angle is, the arm is presently located. It should be here, you move it here, and the complementary filter should respond essentially immediately. Any questions about that? The estimation stuff is a blast, by the way. I hope that some of you sort of get really tickled by it. Like I said, you can go forever with it. This is not the best estimator that we might have done. Many of you have probably heard of Kalman filters or implemented Kalman filters. We could deploy a strategy like that here. Okay, Kalman filter being an application, an optimal application of Bayes' rule, discovered by Laplace. Bayes' rule, that is, not the Kalman filter. Okay. Got 5 minutes remaining. What do people want to talk about? You want to talk about the complementary filter? Is this stuff making sense? Want to talk about some project ideas? What do people think? How about some project ideas? Does anybody know what they would like to do? Aiden, what are you going to do?
I would like to fix the LEDs in the clock faces.
You might be aware that Aiden is a chimes player. The clock tower, you might be aware, changes colors periodically throughout the year. It's red for Valentine's Day, turns on at night so you can see the clock face and so forth. Apparently it's the case that that system requires an upgrade, so the thought is to build a new LED interface to the clock tower. That would be awesome. What else are people thinking? How about just general flavors of projects? Is anybody thinking video games? Yeah? Anybody thinking musical instruments? Synths? Bruce?
I've seen a few nice projects where people would build a scale model of a flute and then simulate the sound of the flute so you play it physically as you would a real flute because it's synthesizer. See people turn a trumpet into a MIDI controller. There's nice thing about music projects is they demo really obviously well. Or poor. So they demo. It's really hard to demo and optimize photography.
This, by the way, you've reminded me of something that I wanted to say about your project proposals. When you're thinking through your project proposals, a really good property of a final project in this class is one that has demoable milestones. So have some ultimate objective in mind, but in your proposal, I'd like for you to think through how you're going to build this thing by way of demonstratable milestones. We'll get this working. When that's working, we can demo that that's working. Then we'll get the next thing working. We can demo that that's working. The reason for that is, as many of you have hopefully discovered by way of this class, building things can be a little bit unpredictable. It is always the case that something that I think might take me an afternoon ends up taking me 2 weeks. And that's going to be the case for some of you as well. And so if you think through your final project ideas such that you have demoable milestones along the way, you have something like an insurance policy, right? If things don't go precisely according to plan, if something ends up being more challenging than you or I predicted, well, then there's still something to demo at the end of the day. And by the way, the opposite often occurs as well, where you think something's going to be a 2-week effort and you discover, oh my God, this only took me an afternoon, okay? And so it's good to think through these final projects ideas in context of demonstrations. I'll show this, and then I can show this, and then I can show this. Yes?
Just a quick question about the proposal. I saw it in 2 different locations. It said due next week and then due the week after that. I just wanted to double check.
So it should be the case. If it's not the case, it should be due next week. So let's see. The notion is that this will be due the week of your Lab 3 Week 2 checkoffs. Yeah. And like I said, if you'd like to talk through any ideas that you might have about these things, I'd be perfectly delighted to. Come to lab or send me an email or whatever, and we can talk through it. But also, the point of these proposals really is for you to throw out your idea, and it gives us the opportunity to provide you feedback on that idea. And so if you are slightly worried about an idea, submit a proposal about it, right? And then we can use that in order to have a conversation about how we might modify it to something that's a little bit more appropriate for the class. I will just mention too, in the last minute here, in case it's of interest to anyone, almost every year I get at least 1 or maybe 2 groups asking me about drones. Group that would like to build a drone. Historically, I have had a no drone policy in the class because it has this annoying property that you test it, and if it goes wrong, it destroys itself. And when you only have a handful of weeks to build this thing, that's not a great property of the project. So the compromises that I've arrived at with students in previous years is, last year I had one group of students build a drone, but they built it with a hole through the middle, and it would slide up and down on a pole, so that they would constrain its translational degrees of freedom, but control its hover height, and they could turn it. That works, right? Because when it doesn't work, it doesn't destroy itself. But I wanted to also mention that a student in a previous year built some Pico-based drones as a research project for the mechanical engineering department to use in one of their learning studios, their motion capture lab. That still needs some more work on it. And so in the event that any of you really wanted to do a drone, there's an opportunity in collaboration with that lab to work on that drone in that space, which is set up for doing drone work. I just wouldn't advise doing it in 238, in part because it destroys itself, and in part too because it could destroy other things when it destroys itself, like other people's projects as well. We don't really want those flying around the lab. Okay, I'll be in lab this afternoon. I'll see many of you there. I'll see the rest of you next week.